Hello, this is Greg Caltabiano. I'm a board member at Atombeam, and I have with me today Josh Cooper, Dr. Josh Cooper, who is the Chief Science Officer at Atombeam. And we're going to talk today about Atombeam technology, and in particular, the different uses and applications for the technology, and especially why it's so important in today's world. So let's back up a moment and start by talking about AI and generative AI. I think all of you have seen the incredible amount of news that's happening right now about OpenAI and LLMs and foundation models and all of the new things that they can do. And I think the other thing that you've probably seen, which is extremely important to understand, is that this is all enabled by massive amounts of data. And this data needs to be collected, it needs to be stored, it needs to be processed, it needs to be manipulated. And this is placing a tremendous amount of stress on the entire technology infrastructure. Just to give you a sense of the scale we're talking about, OpenAI and other foundation models have trained on all the data that's available in the internet. ChatGPT-4, which is the latest model from OpenAI that is now out, has 1.8 trillion parameters. The next model could have as many as 5 trillion parameters. And understand the only way that computers can process this type of data is by having thousands and thousands of computers working together to process these models, process the model, process the data, to train the model, to use the model to do inferences. In order for thousands and thousands of processors to work on the same data, data needs to be constantly moved and stored in a very, very high speed way. The technology industry has responded to this challenge, and you've seen companies like NVIDIA have become among the few most valuable companies in the world. They're a multi-trillion-dollar valuation company. You see other companies like Broadcom that are more focused on the data transport and networking, also become incredibly valuable. But these increments of technology are still struggling to keep up. So there are complementary technologies, and one of the very important one is from Atombeam, where instead of just making the processing factor faster, the storage denser, you actually take the same information and in a very clever, using clever mathematical algorithms and techniques that are very much from the perspective of AI themselves, compacting this data, encoding this data in an intelligent way so that less bits need to be processed, transported to work with the same information. And that's what we're going to talk about today. So first, let's give a quick overview in more detail of Atombeam technology. So Josh, before I start, Josh is a mathematician by background. He's the brains behind a lot of the technology we've developed. He's a MIT graduate, a PhD from the University of California at San Diego, a professor at the University of South Carolina. And he's going to go into professor mode here a little bit and talk about the basics of the technology. How does this work? It sounds like magic, but how does this work?
Yeah, thanks, Greg. Of course, we have a few different product offerings at Atombeam, but the main one that we're talking about today is NURPAC. This is a kind of different take on data reduction. Of course, viewers are probably familiar with compression. That's a rather old and mature space at this point. But we approach it from a different angle. So the thing is that when you compress data, generally speaking, although the goal, of course, is to reduce the number of bits involved, you have to bake in the decompression instructions into the file or the stream that is output of the process. In addition, it's not particularly effective below about a kilobyte in data. So NeuRPAC is able to take data that's sometimes even down to we've done down to 4 bytes at a time, and we call compact it. So we're able to compact that data, shorten it, abbreviate it essentially, and not have to include the instructions for unpacking it, which means you can really take advantage of this shortening even at very tiny lengths. And how do we achieve that? Well, there's a pre-processing stage. So the sort of heavy computational lift is offloaded to a pre-processing stage where we learn from representative data. Of course, this is the big paradigm shift in modern computing. Instead of hard coding algorithms that an expert comes up with, we're going to take a bunch of data that represents what the user expects to see and try to learn patterns from it. So the user provides some representative training corpus, and our training engine ingests that information, learns the patterns that can be exploited for abbreviation, and then exports to the encoder and decoder end of the process a codebook, which is then used when data comes in order to transform it into a shorter stretch of bits.
Well, this is exciting. Tell me if I'm wrong here, but it sounds like in order to enable AI and IoT and all of these data intensive technologies, we're actually using a page from the machine learning AI book and training on the data, and not hard coding algorithms, but actually training on the data, and that training informs how that data is compacted.
That's exactly right. Yeah, it's sort of coming full circle on the paradigm of learning from data, machine learning. That we're taking these methods, have come up with new methods, and we're borrowing other techniques from machine learning, broadly understood, in order to learn how to reduce our data including in AI context. That's right.
Very interesting. Yeah. So just to make sure I understand, and that everybody understands this. So if you compact this data in this way, so the same information can be same without any loss, can be sent with less bits. So this is equivalent to faster transmission
That's
of the
right.
information because you don't need to send as many bits, which translates to less power, less capital equipment, less storage, of course, less processing. Am I missing anything? Because this sounds like a monumental savings.
Yeah, it also confers all kinds of performance advantages. So not only are you getting literal savings out of the bandwidth requirements and storage requirements, et cetera, but you're reducing congestion in a network and therefore maybe impacting overall performance or cooling costs, or there's all kinds of knock-on effects that have to do with improvements of performance conferred by just having fewer bits in flight.
That's great. So let's like move to specific applications and use cases for this. So the first one that we tackled, and the one that probably is most obvious, is for IoT, Internet of Things. So you have examples where there's remote equipment and the transmission is happening over satellites.
Yep.
So the amount of bits you can send are more constrained. Bandwidths are more constrained, speeds are more constrained. So this type of efficiency is incredibly important. Can you talk a little bit about some of the early applications, what types of very specific use cases there are in this area?
Yeah, so the world of computing, of course, is changing quickly, and one of the things we've seen emerge in the past decade or two is the increasing dominance of M2M, machine-to-machine communications, where, for example, in IoT, which is really where you see this perhaps the most, you've got thousands of little sensors just spitting out short bursts of data. I mean, really short in some cases, a single number, a sensor reading, that kind of thing. And it turns out this is exactly the kind of data where Atombeam technologies shine. So that it's a relatively low entropy rate, that it's time sensitive. You don't have time to sit around and accumulate information in order to compress it. You've got to send it right away and use it. So yeah, we've had successes with a number of different vendors and in different verticals. Early on, we had a lot of success with some trucking that was using uh, mobile communications, and were taking a huge hit financially for the communications. Took the every time they turned the device on, it was three messages they were sending. We reduced it to one, um, and took a huge bite out of that bill those folks were paying. We've also had a number of successes in oil and gas, working with companies that are monitoring various kinds of devices that are out in the field and are difficult to keep an eye on. They've got all kinds of monitoring systems and AI keeping an eye on those things. More recently, well, actually the oil and gas is recent, but also we've been working with Ericsson and Viasat in order to have similar impacts, right? So reduce the number of bits moving around over the network, and thus reduce the satellite costs involved with all the communications that where we can be installed.
So for companies like Ericsson and Viasat, they're systems makers. So they use us as part of their systems. Is that the way it works?
Yeah, so our technologies are really an ingredient in a much more complex tech stack. So the idea is that the user, like those folks, are able to take Atombeam software and integrate it into a much more complex system that's handling all kinds of messaging and dashboarding, et cetera. And we're entering at essentially at any point where there's communications, where there's data that's being sent that has this that sort of qualifies that is high demand, you have low latency tolerance, and has a relatively low entropy rate, and isn't already compressed, for example.
Yeah, I imagine that the military is quite interested in this, and I understand that there's been some discussions and some success with the Air Force and with the Space Force because those parts of the military are very dependent on satellite communication, and the ability to communicate quickly, efficiently in very difficult environments is so important. Can you talk a little more about what they were looking for and how Atom Beam's technology really fits what they need?
Yeah, so I mean, generally, the idea is you could reduce communications between, a fighter plane or various devices, communications devices, and the frameworks that they're attached to in the field, back to somewhere where analytics are being performed, or intelligence is being gathered. So we've been able to help in a number of ways. Reduce the communications between a point out in the field and somebody back at headquarters watching what's happening, and sending out responses. Actually, relatedly, we've got so all of the technologies we've been talking about so far are lossless. We've also got a product arm working on some lossy technologies, and that's also sparked quite a bit of interest for DoD customers. Because of course a lot of the data is imagery, is video, things like that. And in those arenas we can use similar insights, different strategies, but similar insights paired with NERPAC and some of the technologies that have come out of NERPAC, in order to have a big global impact on their throughput, data throughput.
Yeah, that's very exciting. So let's move to another area, um, and that is um, data center, mostly data center to data center communication for resiliency and for replication. So just to give some context to the viewers, when companies are doing applications that generate very critical data, think about such as an ERP system or a CRM system or a human resources information system. There's critical data that's created constantly by the organization. In order to make that safe, this data is replicated. in relatively real time so that there'll be multiple copies of all of the information that you've created. As much as possible, that data is stored in geographically dispersed data centers. So you don't want to put it in the same place so that if you have an earthquake or a flood or God forbid some type of geopolitical conflict, your data is safe and your data is up to date. But what's that has caused is there's a constant flow of a very large amount of data now that is moving between geographically dispersed data centers. And the accumulation of this or the total of this data is quite substantial. So, Josh, could you talk a little bit about this use case and how the Atombeam technology can help make this uh, achieving this much more economical and much more efficient?
Yeah, absolutely. So, one aspect of the sort of milieu you're describing is the enormous burden of shipping the data around. You've got to get it from the place where the data is created to this data lake where it's being stored or the servers scattered around the world. That's a tremendous burden, and famously, it's often the case that it's more economical to simply put hard drives in the back of a truck and drive it to the location because of the burden placed by such a volume of data. So we can have an immediate impact on this because all of that data can be compacted. And you apply NERPAC to it, it means fewer connections needed, less on time for the networks that are actually passing the information around, and big impacts on the economics of running even just the shipping of data out to these data centers. Of course, when it arrives, we're using, we're creating a situation where fewer hard drives are needed, or whatever the storage infrastructure and the cooling associated with the infrastructure. It's all these capital investments the expenses are reduced because you simply need less room to put the data. Now, of course, again, compression's been around a long time, so there's this question: why not just compress the data and put it out there? Well, a couple of problems with doing this. One is you can't generally edit compressed data. So this again gets to the data rate issue or bandwidth issue that if the user's got a huge file, a compressed file in the data lake, and you need to update it, probably the whole thing needs to be updated. But that's not true with NERPAC. So if you have a NERPAC encoded data, it can be edited in small sections. So the idea is that the user could only send deltas, could send small changes, so that you don't have to send the entire compressed file all over again. This also has another interesting consequence in terms of the utility of the data. We've heard from a few companies we've talked to over the past few years, especially those that are maintaining, for example, large pools of logs. This is something where 99% of the time they're not even touching the file. It never gets seen again, but it has to be stored for legal purposes or because you can't anticipate in advance what's going to be necessary. So the idea is again, you could compress it, but then it makes it really hard to use, hard to search. So if you're looking for a particular log file with a particular timestamp in it, you got to go one by one through all these compressed files and uncompress them and look inside. It's very computationally intensive, it's energy intensive, and it's maybe more than anything important, that it's time intensive. It's just it takes a long time to search that data. And to even to return the results, because then you have to decompress it all. Well, with Atombeam compaction, with NERPAC, we're able to read the data at rest, even though it's in compacted format. So you're getting this massive reduction in size, but it's still searchable. You could still go looking for that timestamp in the data without having to unpack everything. And then once you find it, you can then read the file around it. without having to unpack, a thousand other files that happen to be packaged with it in that whatever batch was collected for the purposes of compression. So there's a number of different ways that we can impact, remote data centers and large data warehousing operations by reducing the communications between the place where the data is created and the storage location, reducing the requirements at the storage location, and then keeping things usable and accessible to those who are putting the data there.
Yeah, this is really exciting. And I think just to make sure everyone understands, while there's been huge strides in bandwidth, in creating more bandwidth between data centers, between geographies, it's still limited. You still have a certain amount of bandwidth in undersea cables. Very often, as we've seen recently in the news, these undersea cables are damaged, and you need to rely upon satellite backup. So this type of compaction becomes extremely important. And as the data volumes increase, it becomes increasingly important. So it's a very exciting area.
Yeah, absolutely. And of course, whenever you provide faster pipes or more pipes, they just get filled right away, right? The users
Absolutely.
always fill this stuff,
Absolutely.
right? So it's not like we're
Yeah.
solving the problem by providing more bandwidth. It's that the problem's always going to be there because the user's always going to want to use up the space that they've got.
Yeah. So let's go to another related use case, and that is the communication between processors. So data centers are made up of thousands, sometimes tens of thousands, hundreds of thousands of processors. And they're not all doing different things. Very often they're working on the same problem, different parts of the same problem. So communication between these processors is extremely important, time sensitive, and very reliability sensitive. You can't compress this data, lose some of that data, and expect the calculations to work. So data needs to be, if data is manipulated and compacted, it needs to be lossless. So there's communication happening within components, what are called chiplets, which are very small processors, multiple processors put inside one processor. A good example is if you look in NVIDIA, AMD, and even Intel, inside their packages are many, many processors. Those processors are transferring information constantly. Then on a server board, there's many, many packaged processors, each of which contains many processors. So there you have information moving back and forth. And of course, between servers, the thousands and tens of thousands and even hundreds of thousands of servers, you have information flowing at very high speeds in very critical, time-dependent, latency-dependent situations. So Josh, could you talk a little bit about how Atom Beam technology could be used in these types of applications and why it may become increasingly critical?
Yeah, as you described there, there's sort of every level of communications happening, whether it's inside a chip between logic units to chiplets to between boards, between servers, even between whole computational or data warehouse locations where that need to be in communications because they're processing the same data or trying to perform some massive operation in parallel. In all of these contexts, essentially, we can have an impact on the bandwidth demands, on the energy costs associated with all the different communications happening at those levels, because so much of that data is fairly low entropy rate. It's something where there is room to squeeze it down to less. But historically, the solutions to do this have been too costly in terms of latency, in terms of time, and also in terms of the computational complexity of the stack. Sometimes the devices where you'd like to be compressing or decompressing or simply can't handle that. It's too much of a computational lift. NURPAC was designed from day one to be an ultralight lift computationally. So this means you could burn it into a fairly small number of transistors at the exit from a chiplet and the entrance to the next, reducing the the overall time it takes to send some data because you can send it in fewer packets, and reducing the power demands of the system that needs to be facilitating the movement of bits around. Yeah, it can have all kinds of effects on both the costs of the devices and of running the devices that are performing routing at all the different levels you're describing, and also improve performance when it goes live because you're able to reduce congestion and improve the number of times or reduce the number of times that traffic jams happen.
Yeah, and this problem is just getting worse and worse. In fact, my understanding is that as these new chips come out from companies like NVIDIA, they take more and more power, and the power makes the data centers take in so much power that right now many communities, many countries are extremely concerned about this. So the beauty of the NeuroPack technology is that it's a way to do this processing without having to increase the amount of power, the amount of capital equipment.
That's
And
exactly right. Yeah.
that's very unique, very exciting, very timely.
And we see it's pretty much every week I see some major article about the walls that are being hit in all these different contexts where we
Right.
just the demands of all the new technologies and new computing paradigms are running up against all kinds of constraints.
Yeah, especially the laws of physics. As the processors go fast, have faster cycle times, clock times, as the network switches have faster clock times, that increases the power of those chips, the power usage of those chips, which is expensive, very really difficult for these communities that just don't have the power or the electric grid that is set up to do this.
Yeah.
Very exciting. Let's shift again to a very exciting kind of family of use cases, not just one use case, which is for the training and the inferences of the foundation models, the LLMs themselves. Because LLMs are basically manipulations of information. And if that somehow that information could be represented in a way that has less bits, then more could be done with that information with less capital. Could you explain that in more detail and the
Yeah.
various ways that that could be implemented?
So I should start by saying that every time we sit down to look at this, use cases in AI and ML more generally, we find new places where atom beam technologies can make an impact. Because the world is changing very quickly in the space, and there's so much data flying around that's needed to run these different operations, whether it's an app on your phone or a massive training operation happening in a data center for a large corporation. We can have all these impacts. For example, the training data. So all of these models need to learn, what is English, or whatever language they're operating in, or learn from a bunch of time series data how to make predictions, learn from images of the weather, how to what to guess about what's going to happen tomorrow based on what's going on today. This requires a tremendous amount of historical data that is used to train these systems, and the process of training is computationally outrageously expensive and requires just equipment that is eye-watering in its scale. Just absolute boggling numbers about how many processors and machines are needed to make it happen. The thing is that if you compact the data, well, then it's possible to store less of it. That is just literally the number of bits is fewer to train the same fidelity of machine learning model. You can pass that data to the engines that are going to learn from it more easily and more quickly because it requires fewer packets and lower bandwidth requirements. So all of these training operations can be assisted by NURPAC because you literally just reduce the number of bits required to be passed around. It's absolutely enormous, the amount of data that's being used to train on for these things. And there's a number of other ways that we've discovered that Atombeam can help in these different situations. So, for example, even the models themselves can be reduced in size if you can compact the training data. So the thing is that these neural networks, massive deep neural networks, are able to learn as long as the information is there. And so, well, if you can compact the data and pass along the next several lines of text or whatever it is that you're learning from with fewer bits, that potentially means a smaller network. Smaller network means cheaper equipment, lower energy costs, and lower bandwidth demands. Or conversely, for the same amount of bandwidth, the same amount of processors, et cetera, you could do that much more. You could learn on that much more data or have that much more sophisticated features in your AI agents or whatever it is that you're training. We recently realized that it's possible to compact in a way that downstream can help the models to perform. So it actually means that, for example, random forests or various kinds of gradient boosted models can operate more efficiently because we're able to provide the relevant data to those models more compactly, just literally fewer bits. So there's all these steps along the pipeline in AI, very complicated pipelines, from ingestion of data to cleaning of data to sending it along, training on it, and then ultimately deploying the models that can be impacted by using compaction, NURPAC, to reduce the number of bits involved. I should mention one of the ways that this could be done is that in all of these machine learning settings, once you deploy a model, it's a massive computation every time you try to run data through it. And this generally speaking, people are thinking about spreading the computation out. Federated learning is one of the ways this is done. There's a number of different paradigms. And I mean, it's such an important bottleneck in being able to use these incredible new technologies that there are interconnects, like optical interconnects that are available. People are spending $30,000-$40,000 on each of the interconnects just to be able to ship data between layers of a model more efficiently. Well, again, this is a place where Atombeam NURPAC can come in and reduce the number of bits that have to be moved and make it faster so that you're able to get data from the first half of your neural network to the second half more quickly, or get it out to the user more quickly, or like I said, reduce the size of the model itself so that it could be run on a smaller device, like a mobile device or some other more limited device than your typical heavy-duty machine that's used in machine learning contexts.
Wow, this is a huge number of implications for this technology for LLMs and AI.
That's right.
Josh, are there any other areas where you think we've covered so much, but did we miss anything that you think is important?
I think we've missed a lot, but we don't know what they are yet. So yeah,
Yes, yes. We're always learning as companies come in and say, can you use your technology for this? Can you use it for that? Whether it's commercial companies, military. So this is a very exciting time. And we're in a world now which is defined and enabled by data. And so it's the right time to be doing this type of technology.
that it is.
So Josh, thank you so much for your explanations. And for letting everybody know how this technology is being used and how it actually works. Thanks everybody for listening.
Thank you.